MP. Thank you for being here. So before I talk about this one candidate that I think is really interesting, maybe let me tell you a little bit about tidal disruption events and also the efforts that we have been doing in eROSITA to uncover new sources. Okay, this means yours. So when we talk about tidal disruption events, I always like to show this video, although Zoom is very bad. But basically, you have events consist of a star which is going too close to a supermassive black hole, and the gravitational pull stretches it until eventually, in the tidal disruption radius, the star is completely destroyed and then subsequently gets accreted. Yeah, this is usually more impressive than this, but yeah, but I think it's very cool, and it's always nice, I think, to remind us what these events look like and why we also want to study them. Okay, so of course we are talking about transient events because stars have a finite amount of mass. So as the accretion happens, eventually it will end, and they are transient on timescales of a few months. So basically, what they look like is we have a rise. We can see them both in the optical and in the X-rays. We have a rise which lasts on a timescale of more or less 1 month, and then a decay which will evolve over timescales of a few months. And here's what they look like in optical light curves. And here is some example of what X-ray TDs also look like. And already here I think from the number of sources which are populating this plot, I can spoil to you that there is a bit of a bias towards optical tidal disruption event compared to X-ray selected tidal disruption events. And something that's quite interesting about these sources is that sometimes they will flare in the optical and in the X-rays. Sometimes they will only flare in the optical, sometimes only in the X-rays. And even when they do this simultaneously, it's not obvious which one of these two phases comes first. And this overall is something that is still quite unclear in our understanding of tidal disruption events. Sorry, I'm not sure the slides are in the correct order, but okay. Well, then I'm going to skip it. And so the fact that we have this shift sometimes in the X-ray emission and the optical emission, and not all the time these two come together, makes us very much unclear still on the origin of the emission. And in fact, in all models, we have that a star is getting disrupted as it enters the tidal disruption radius, and then half of the material is bound to the black hole. And in the first family of models that was predicted, basically the bound material is very fast at circularizing, and so it forms an X-ray emitting accretion disk. But then you have all of this debris from the star, and overall, the X-ray emission develops winds. So you have a large reprocessing layer which will process the X-ray radiation into optical radiation. However, this model, although it seems to explain some of the observational features, has a big problem, which is the timescales of circularization. So you can see in the scheme that the orbits are quite elliptical for these events. And in order to dissipate energy to go to a circular X-ray emitting accretion disk, you need a lot of time, actually. And that's why the second family of model was actually introduced, in which instead of the quick circularization, you have a second pericenter passage of the bound debris, which then experiences precession and shocks itself. You can see this here. This is called the stream-stream collision self-intersection. And this shock produces optical and UV radiation. This depends on the relative velocities of the flows. And it's a great way in which you can actually dissipate this energy. And then only later on, you can produce an X-ray emitting accretion disk. So this would predict, I think you can understand, first the emergence of optical radiation and then the emergence of X-ray radiation. And right now, even though we have some evidence pointing that this model might be working, we're still far from understanding what's happening. And that's why studying these events is quite interesting. And since my slides were in the wrong order, I'm going to go back a little bit. But some other reason, if you don't care about accretion, why TDs are very interesting, is because they allow us to probe the smaller end of the supermassive black hole mass range. So the tidal radius, which is written here in this cartoon, scales with the cube root of the black hole mass, while the Schwarzschild radius grows faster. So this means that above a certain mass, the tidal disruption will happen inside of the event horizon. So actually the black holes which are preferred to be revealed through tidal disruption events are low mass supermassive black holes or intermediate mass supermassive black holes. Okay. So as I was showing you before in the plot regarding the optical light curve and X-ray light curves, from a historical point of view, the first candidates were discovered with Rosat in the X-rays, and then a few more candidates were discovered with Chandra and XMM Newton serendipitously. But then with the advent of optical surveys, you can see here the cumulative number versus the year by band, ZTF, SAS in Atlas. You can see that we have an overabundance of optical tidal disruption events, and the X-rays have been very slow to catch up to find new events. And since sometimes you only have X-ray emission, it's quite important to have an unbiased view. So we are very lucky that we actually had eROSITA, which Andrea told us the time domain capabilities of, to find new events of this sort. And since Andrea already introduced the observational strategy of eROSITA, I can go a bit quickly about this plot in which I describe to you how we can actually find these events. So basically, we have 4 and a bit surveys that were post-sky surveys that were performed by eROSITA, and what we look for is for events that were not detected in one eROSITA or sky survey, but then appear in the next one and then fade. And here, all the irises have been expanded into their eRO day, we call it light curve. And you can see that this is an example of an event which was discovered, which the counts were comparable with background in eRASS1, but then we have an obvious excess in eRASS2, which smoothly decays in eRASS3 and eRASS4. If we apply this strategy, we can find a lot of new transients. And in particular, I want to sponsor this catalog, this eRO Extra, which was work done by Yulia Grotova, another PhD student in the high energy group, which selected a sample of 304 extragalactic non-AGN transients. So she did a lot of cuts in order to remove anything which could be classified as an AGN prior to the eROSITA outburst. These sources are only selected as being variable between eRASS1 and eRASS2, and then the rest of the light curve, the counterpart analysis, and also the spectral analysis is provided in this catalog. So very, very interesting sample from which you can go and actually select a tidal disruption event golden sample, from which we found 32 sources actually. And this was done by using canonical TD selection criteria. We were discussing yesterday how maybe canonical selection criteria are not really a thing in tidal disruption events, and everybody does a bit what they want. But in our case, this referred to monotonically decaying light curves, so either rising and decaying or just decaying, with soft X-ray spectrum, which are typical of TDs and exclude AGN in addition to the previous cuts that were done. And this resulted in 32 sources. And if we add them to the 13 sources that were presented in the paper by Sazonov of 2021, from the Russian part of the eROSITA collaboration, we arrive at 45 sources. And if you look at these numbers, which here, now we have a bit more than 100 tidal disruption events, 45, quite a significant number. So we're finally starting to fill this gap. And what you can do, since Mara was saying how we are a catalog-based collaboration as well, is to do population study. So an example of what you can do is the X-ray luminosity function. Here you can see the golden TD X-ray luminosity function, which has the same shape as a gray line, which instead is the optical luminosity function. There is an offset though in the normalization, and this is quite interesting. We have to understand if it's an intrinsic offset, an observational offset as well. This is still a very open question, very, very interesting. And you can also understand properties about the host galaxies of these tidal disruption events. And in this study, if you look at the blue point with the hollow markers, the white markers, which are the ones with good redshift, if you plot the stellar mass versus the color, you can see that these align with the green valley, which agrees with optical tidal disruption event studies, not so much with mid-infrared tidal disruption event studies. So again, more information to add to the overall understanding of these sources. eROSITA is not only interesting for finding new sources, but the fact that it has time domain fluxes for each part of the sky allows you to add additional constraint to any new sources you can find. And this is an example which was presented also yesterday of this intermediate mass black hole TD candidate, which happened here, which was detected by Einstein probe at the beginning of last year. But when we looked at the eROSITA light curve, we can actually see that there was a detection which maybe contained a hint of a rise. And this is actually very interesting because it could be used to add additional constraints on the black hole mass based on the circularization timescale, which agrees with the other mass estimates, which are around 10 to the 4, 10 to the 5. So very, very interesting that we also have this additional data set for all positions of the sky, well, half of the sky.
And I say that is the speed that I was discussing before. That is the object for which we find a counterpart of very low probability, but it was the right.
Thank you for this. So you cannot only do catalog studies, but you can also find very exotic and new sources with eROSITA. Here I have a plot in which I show the size represents the flux of the peak of these new sources, and we have plenty of sources which were published in the past. Very, very interesting TDs. This is another Bowen fluorescence flare, actually, repeating partial TD, the best repeating partial TD candidate so far. And today in particular, I'm going to tell you about this very faint one here. I should stop showing this plot. It's a bit humiliating. But it's called eRASSU 2026. So this is a new nuclear transient which was discovered in eRASSU. This source was undetected in eRASS1, and it is indeed part of the ERA-Extra catalog. Satisfies all the criteria to exclude previously known AGN, so wise color cuts. And it also has a very nice soft X-ray spectrum. But I will show you in a second why it doesn't fit in the golden TD example. It was located in the nucleus of this galaxy, so we're quite confident also from an energetic point of view that this is an event related to a supermassive black hole and not another type of transient in galaxies. And what's really interesting is that optical surveys did not detect a significant flare from this source. So it would have been missed. We're very happy that we could actually find this because it adds a lot of new features to the overall ambiguous nuclear transient population. For example, we have X-ray short and long timescale rebrightenings, transient lines, which include iron-2, coronal lines, helium-2, Bowen lines, triple peak H-band, a lot of things, which I'm about to show you. But let's start from the light curve. So as I was telling you, this source was undetected in eRASS1. We have the X-rays here, the mid-infrared and the optical. And we're going to go through each one of them individually. It was undetected in eRASS1. But then in eRASS2, it became bright and we had the discovery and it started decaying as well. And our first swift follow-up observations agreed with this. The spectrum was also very soft, so this was a very good TD candidate. And we kept on following it up. As you can see, soon after we started seeing rebrightenings, the eRASS4 one does not show rebrightenings, but then eRASS5 shows yet other, like more rebrightenings. We had several follow-up observations in the X-ray after. This is our deepest one, although we have more observations from Einstein probe, which would push this upper limit down as well. And the source was never detected again in the X-ray. So the overall evolution was confined within a span of 2 years. When we look at the infrared flare, we can see that we have a long-lived dust echo. So again, living on a timescale of more or less 2 years. And I call it a dust echo because it's peaking coincident to eRASS3. So the X-ray flux is going down, but this X-ray radiation has hit a dusty material, which then processes it to infrared wavelengths. But then because of the light travel time, we see that the peak is delayed by a few months, more or less 6 months. And when we look at the optical inside, we're not really sure what's happening. This is quite a low intensity flare. We had to do difference photometry on Atlas because we didn't have access to any other surveys that found the flare for the source. And maybe there is a weak flare happening here. Actually, probably yes. There is definitely a decay happening that we can see after the last eRASS5 flare. And maybe some hint of a pre-flare rise. So quite interesting as well from an optical point of view. And as I was saying, we don't only have rebrightenings on a longer time scales in the X-rays, but if we expand all of the ERASs in their light curves, you can see that ERASS3 has definitely some flaring happening and eRASS5 even more significantly. And this is recurring over, I mean, in this case, the time in between the two flares is 16 hours. It's not QPs. We looked very much to see if we could confirm the presence of QPs, or if there were QPs, they're already gone. Don't ask me about the QPs. But what's really interesting, I think, is the optical properties, the spectrum. So even though we don't see a clear flare, when we took follow-up optical spectroscopy, we could see a multitude of features. So first of all, you can see iron-2, very prominent Balmer lines, and then iron-10, you can see it very well here, and also iron-14, very prominent. And comparably not stronger than oxygen 3. So this classifies this resource into the extreme coronal line emitter classification, in which basically the coronal lines are stronger than the oxygen. And these lines require very intense oxidation potentials to be produced. And these have been interpreted as tidal disruption events in gas-rich environments. So another indication that maybe we have something like we're dealing with some exotic tidal disruption event. And you also, maybe I should point out that this is the archival to the spectrum from early 2000s. We don't really have anything here. There's not much. We only have galaxy lines, even though the spectrum was targeted on the nucleus of this galaxy. And some other features which are very, very interesting are these helium-2 lines and these Bowen lines, Bowen fluorescence. Bowen fluorescence is a process in which basically in presence of extreme UV or soft X-ray flux, you produce helium-2 Lyman alpha photons, and then these go and excite oxygen 3 and nitrogen 3 positions, which then cascade down until you produce all of these lines, which are colored here, overplotted onto the spectrum of a tidal disruption event. These are very common in tidal disruption events, and actually they're considered one of the smoking gun signatures. They were expected actually in AGN as well, but they have not been found in normal AGN unless they're flaring. So this also would be suggesting that we are dealing with a tidal disruption event. So is it a tidal disruption event? Well, when I plot the spectrum of JO1 2026 compared to some other tidal disruption events which show Bowen lines, I think you can see that they don't really look similar. Even though we have the transient nature, the soft X-ray spectra, no prior evidence of AGN activity in these lines and the extreme coronal line emitter classification, this together with the rebrightening don't really make sense into a tidal disruption event context. And indeed, the lines of tidal disruption events are much broader than the lines that we're seeing here. We're talking about 10 to the 4 kilometers per second. Very, very broad because we have outflows and also collisional broadening, which is at play, while in our case, we talk about narrow line CFER1-like widths of these emission lines. And also, J1 2026 is quite long-lived, and the rebrightenings are not really something that we expect from TME. So what is J1 2026? Well, from a phenomenological point of view, it is a Bowen fluorescence flare. In fact, here in green, I'm showing you an example of some Bowen fluorescence flares that have been found, which is a phenomenological classification, right? And you can, I think you can see the width of these lines are much more similar to the ones that we're seeing here. Also, these lines are more long-lived, just like in the case of O1 2026 compared to TDs. And the mid-infrared flares are usually also stronger. So this class, which was identified by Baldini, we only have about 10 sources so far. And Pajana is going to show us another one. And some other similarities that we have between O1 2026 and this class is that most of them show strong coronal lines, who are also classified as extreme coronal line emitters. And what's really interesting is that 3 of them show clear previous indication of AGN activity. So in fact, the interpretation that was first proposed is that these are rejuvenated supermassive black holes. So you already have some sort of broadline region-like structure around the supermassive black hole, and then a sudden enhancement in the accretion rate illuminates this broadline region, and that's why the Bowen lines have these widths which are more broadline region-like than outflow-like. Although we still don't know exactly what could be the origin of this sudden enhancement of accretion, and we can talk about accretionist instabilities, more gas flowing onto the supermassive black hole, and other possible ways in which we enhance the accretion is through tidal disruption events. And indeed, if we assume that this is due to a tidal disruption event happening in a gas-rich environment, which is what's suggested to us by the extreme coronal line emitter, we can make a bit more speculation on the nature of the source. So some of these Bowen fluorescence flares, I mean, most of them are characterized by an optical rebrightening. And for half of them, I would say, it's about 1 or 1.5 years after peak. And I was just checking now, the ones that have the rebrightening after 1 or 1.5 years all have the same black hole mass. So maybe there is something there. And indeed, these are an example of 2 of these Bowen fluorescence flares. This is not, but initially it was identified as maybe a similar source. You can see the rebrightening happening on this time scale. And something that is pointed out by this paper, came out in 2024, is that the optical amplitude of the rebrightening, you can see here, anti-correlates with the strong strength of the X-ray radiation, which is coming out. In fact, the shaded area represents where X-rays are detected. So basically, stronger optical rebrightening, less X-rays, weaker optical rebrightening, more X-rays. So according to this paper, this could be due to a viewing angle effect if we're talking about tidal disruption event. And I want to point out that maybe the more long-lived rebrightening in eRASS5 of J1 2026 seems to be happening on the same time scale. So what if it is actually connected, but just we're seeing something from an X-ray point of view rather than optical? Indeed, in this scenario, since we don't only have an AGN unified model, but also a TDE unified model, stronger optical rebrightening means that we're looking at objects more edge-on, because the X-rays are completely obscured from the outflows and the reprocessing layer. While the more that we go face-on, the more we have access through this funnel through which X-rays are free to be released. And so indeed, in this interpretation, this source with the weakest optical rebrightening is seen a bit more face-on than the other. And in this case, J1 2026 would represent a fully face-on event in which we're seeing directly the X-rays and we're not seeing strong optical rebrightening. And this would also explain the X-ray short time and long time variability, because we would have access to the innermost part of the X-ray emitting accretion disk. So instabilities that we know are happening in accretion flows would just show up without any type of reprocessing to smooth them down. So this would also work. And if you want to look at additional evidence that we have, or this is just another scheme in which also the presence of iron agrees with the face-on indication. But if you want to see about additional evidence, and maybe we're looking at a face-on geometry, one on the spectrum, we have a triple-peaked H-beta profile. This is quite peculiar, but it has been seen before in tidal disruption events, also in changing looking GN. And while the central line is just a galaxy H-beta emission line, the more boxy and double-peak profile can be modeled as being produced into an elliptical configuration of emitting gas. And if we associate this to the tidal disruption event, we can model this, and we can get an inclination angle for this distribution, which in our case is 10 degrees. So basically, you are, if we trust this model, this is indeed based on geometry. So we have additional evidence that this might be the case. And with this, I will leave you with my conclusions, in which I guess the main thing, J1 2026 is a very cool source, which is new, and it was discovered in the X-rays, but would have been used by only looking at optical surveys. From a phenomenological point of view, this is an extreme coronal emitter and a Bowen fluorescence flare. So we're adding sources which are also breaching these two specifications, which suggests that maybe we have a pre-existing broadline region-like structure. And in a possible interpretation, we are having a tidal disruption event, which is triggering this enhancement of accretion, in which in this case, it would be seen face-on. So overall, we are very thankful that eROSITA has opened this space for new discoveries, and we are advocating also for more time domain X-ray facility. And yeah, I'm ready to take questions.
I start. I still have the same question I asked you a couple of weeks ago when you were in Bologna about the difference between the Sazonov luminosity function of TDE and your luminosity function.
Can you remind me the question?
The
Remember a
function.
Valley question.
No. The luminosity function. So how can you explain the difference between the Sazonov luminosity function and your luminosity function?
Yes, that's true. So the Sazonov luminosity function, I don't know if you can read from here, but the red points. So the way that these sources are selected is a bit different. The Sazonov sample was compiled when the eROSITA was still ongoing. So it only used eRASS 1, 2, and 3 at the time, while the golden sample was compiled when the eRASS 5 also was done. And while in the Sazonov 2021 paper, the criteria for which something is classified as a TDE are not super well defined, I would say. We have very clear selection criteria for the Grokova 2025 paper. So this is also adding maybe some differences about which sources are being picked up. But yeah, it's obvious. Like it does seem like we're looking at much more bright events also in the Sazonov function. There's also some correction factors which are included, which might be a bit different in the two works. But this is something that we have to. It's not exactly clear actually to us.
Maybe this selection of Sazonov et al. Is a bit contaminated also from other sources because you don't have the full the eRASS4 data set to.
That could also be like if there is a rebrightening in eRASS4 and eRASS5, these would still enter the. Yeah, so that's possible.
If it is contaminated, it can go down and so closer to your.
Yeah, so I have a question, but I don't expect you to answer. Can you show the spectrum with Bowen? Because what is puzzling me in general in the sources is when you try to model it, the Bowen part, yeah, you add the Gaussians, but then also there is some iron template, but it's only on the left side. On the right side, you mostly don't need it, and it's so unintuitive in general, because when you have AGN, you see it on both sides, and here you just see it at.
Yeah, I mean, we were discussing about this also yesterday, right? I agree. Isn't this kind of maybe related to iron as well? I'm not sure actually, but it's definitely the right part is that's not as strong as in the case of standard AGN. That's
Last one to comment. I think it's the first example among Bowen flares where there is no indication of AGN activity in the archival spectrum. And, 25 days, that's 25 days after what? After
the X-ray discovery. The X-rays have a cadence of 6 months.
We already have something that looks like a BLR. Could you check if this makes sense in terms of the scale of a BLR or what would it tell us?
Well, so the thing is, the rise, I mean, source could have been detected like here already, right? So even 5 months prior to our discovery, maybe even brighter. I think months make sense in terms of BLR sizes. But yeah, but at the same time, something, I mean, this flare rise.
Yeah, actually, I was about to comment about that. Like maybe this is new accretion flow, and we are seeing a TD, like in this starfall, and well, the rate of TDs should increase. Just a proposal. Maybe another new body.
Forming, and then we have this.
Yeah.
It's producing this fall of the star and black hole, which is creating this.
Yeah.
If anybody has more opinions on what this could be, it's very puzzling, I would say.
Is that CTF didn't observe?
Do you have a sense of the UV brightening, just given upper limits versus Swift? Or
yeah, we unfortunately the observations use different filters among each other, so the UV is not well constrained. But, I mean, it's true that we have more observations later on. I can see how it changed over time.
It's a newly formed. It's a totally newly formed accretion disk. It forms inside outward. It will have a much UV stronger kind of an SCD. May give rise to the Bowen thing, to the strong infrared flare. I mean, in a way which is more extreme than stable normal. We have something like an unbalanced, spectrally speaking, unbalanced disk.
Okay, I will check more this Swift data to see if that's happening. Thanks.
Due to the time limit, you have other questions, we can discuss it at lunch.